This is a simulation of the photoelectric effect, which states that light incident on a cathode can induce a current in a circuit. So here you can see we have our light source. It's directed at the cathode here. The material of the cathode can be controlled using this drop-down menu and select any of these options, but we will leave it at sodium for now. The intensity of the light can be controlled on this slide bar here. The wavelength can be controlled here. You can see we can go all the way from infrared to ultraviolet. The current in the circuit we measured down here, and this battery, the voltage is currently set to 0, so we won't worry about it just now. Now, let's start at 0 intensity for our light and the maximum wavelength in the infrared range. So if we push play, we're turning on our lamp, and at 0 intensity, we see no current in the circuit, which is what we would expect. However, let's increase the intensity and see what happens. So we're all the way up at 100% intensity, and we still see no current. Now let's try decreasing the wavelength. We still see no current as we go down through yellow, green. Now right about 500 nanometers, we're starting to see some electrons being ejected from our cathode. When the electrons reach the anode here, they go through the wire and they will be registered as current. We don't have enough electrons for it to register, so let's slide wavelength down a little bit more. You can see now we're reading a current of 0.019 amps. Now this is interesting. The intensity of the light, we increased all the way to 100% and we saw no current. But decreasing the wavelength, now we're starting to register current. We're starting to eject electrons from the material. So clearly it is not the intensity of the light that determines whether electrons are ejected, but the wavelength. And we can prove that by now decreasing the intensity of light. We can see the current goes down, but there are still a few electrons being ejected. So the intensity of the light, we can see here, determines the number of electrons that we're ejecting. So as we get to less and less intensity, we start to see almost no electrons. If we go all the way back up to 100, we're seeing a lot of electrons. Now, the wavelength of the light must determine some other property. So if we continue to decrease it, we can see that now electrons are exiting the cathode with much more kinetic energy than they were at the higher wavelengths. This is a property of both the material and the quantization of energy of the photons, the light particles, that are incident on the cathode. So the energy of light is proportional to its frequency. And we can see here a graph of the energy of the electrons that are ejected as a function of the frequency of the light that we're shining. So as we increase the energy of the light by increasing its frequency, we can see we're also increasing the energy of the electrons that are exiting the material. And as we increase our wavelength, we can see right around where we observed previously, the electrons have 0 energy at this particular frequency of light. So this is what is known as the work function of the metal. When the energy of the light that is incident on the cathode is exactly equal to the amount of energy necessary to eject an electron from the metal, then the electron will leave with 0 kinetic energy, which is what we see at this graph. If we continue to move down a little bit further, we see the electrons are ejected with a much lower kinetic energy than they were when we were up in the ultraviolet range. To return to the ultraviolet, we can see they're moving much more quickly. Now, let's look at the battery that we have down here. The battery can provide what is known as a stopping potential. So if we increase the voltage in the battery in the opposite direction that the electrons are trying to flow, meaning we're creating a potential barrier to the electrons, then a lot of the electrons are no longer able to reach the anode. You can see here how many of them are being deflected by the potential energy. So only electrons with enough kinetic energy to overcome the potential barrier can reach the anode and be registered as current. So we can see current versus battery voltage on this graph here. As we increase the battery voltage, you can see we eventually can drive the current all the way down to 0, and none of the electrons are now able to reach the anode. Now, let's go back to where we were still seeing a little bit of current. Now, if we increase the wavelength, we see that we can again drive the current at this stopping potential down to 0. And this corresponds to what we would expect, given that the kinetic energy of the electrons leaving the material is proportional to the frequency of the light incident on the cathode here.